All right, so I'm going to talk about building real systems with Reason. I think a lot of people aspire to have their day job be in Reason, not just their side projects, not just something that they can tinker with on the weekend. You want to actually build real things that you're shipping to users. Quick bit about me. My name's Sean. I'm coming from San Francisco. I work at a company called OneGraph. I'll talk a little bit about that today. It's built entirely in Reason Native. I ran engineering for a payments company, and my personal background is I used to use Clojure and ClojureScript very heavily. These days I tend to live in kind of a Reason and Rust world. And I want to preface this talk. It may seem like a bit of a downer. It may seem like a little bit harsh. That's not the goal. I have two kinds of talks I give on Reason. I have one where I'm selling Reason to the outside world, and I think there are a lot of benefits of Reason, and I will talk truthfully about those benefits. Then I have the inner circle talk, where I'm talking to the other people in the OCaml world or the Reason world, and I'm saying, this is broken, and these things need to be fixed. So this talk is really about kind of the taming of complexity in lots of different dimensions while trying to build a real product in Reason. And this preface is my way of giving me now free license to say terrible, terrible things. All right, so OneGraph. OneGraph is a very, very simple idea. It's a single GraphQL API endpoint through which you can get GraphQL access to, say, Stripe, Spotify, Salesforce, these kinds of services. We also build a bunch of open source developer tooling around the GraphQL experience. Yeah, so in summary, like, OneGraph is just your kind of standard web app. We take web requests and we respond to them, mainly in JSON. Well, what is a web app? What is a standard web app? What goes into that? Well, in our case, we talk to lots of other APIs. So that means that we need to have a pretty decent HTTP client to talk to those APIs. Also, we want people to talk to our servers. That means we need to have an HTTP server at some point. We probably need the standard things like a database to store sessions, users, any sort of application-specific stuff. We need some crypto libraries, probably, for hashing passwords. We don't store it in plain text. You'll be pleased to hear. We also need to encrypt certain secrets and have them encrypted at rest. We do lots and lots and lots of transformation of JSON and XML. Reason Native by default is blocking. All of the I/O is blocking. So we have to use libraries that make it non-blocking. Otherwise, we would not scale very well. Lots of logging. And then all the other standard stuff. This list goes on for a long time. There's CI and CD, getting this into like a production environment, running it on servers, scaling the servers out, monitoring them. And it feels weird to enumerate all of that, right? Everyone is aware of what goes into a web app. But I think it's important to mention that production services are not islands. They rely on an ecosystem. They rely on those libraries being there. No one wants to rebuild, AWS. No one wants to rebuild Heroku. You just want to push and have your code run. And so whenever you're considering the benefits of some technology like Reason Native, you have to be very clear about what are the costs and do they outweigh or the benefits in this case. And that is especially true if you are betting your success, your company's success, or your team's success on this new technology. So what does this mean in practice? I want to walk through a single HTTP request, the full lifecycle, more or less, and see what does that actually look like. What are the systems, the libraries that it actually touches? I'm not going to go into the details of GraphQL, but this is a single request. Let me make this a little bit bigger in a nice way. There we go. All right. So this is a single request that we might see from one of our clients. This is going to hit 4 different upstream APIs. It's going to hit the npm API to get some information about the name of an npm package. It's going to hit a different npm API to get the information about the downloads on that package. Both of those are unauthenticated public calls. It is then going to join into GitHub, and it's going to say, if there is a GitHub repository associated with this package, I want to know how many open issues it has right now. And that is the GraphQL API offered by GitHub. And we also stitch in the contributors. I want to know who has contributed to this package before. And that comes from GitHub's REST API. And both of those are authenticated requests. So this is kind of like a reasonably standard request that we might see. But you can see it gets translated into a lot of upstream work potentially. So let's start at the very beginning. The HTTP request comes in, and we read that off the wire, and we pull out the cookie header. We need to go and find out, does this user have a session? So we need somewhere to store sessions. And we can store it in Memcache or Redis or whatever. We'll just store it in Postgres. We'll just make it easy. The way that you work with Postgres in Reason Native is via libpq, typically. There are two competing approaches. We use libpq. Now libpq is very powerful. It gives you full access to all of Postgres features. The main data structure that libpq understands is an array of strings. Everything that you send and receive to libpq needs to be turned into an array of strings. This is a fun one. We actually have to process every one of those array of strings and try to figure out, is this a Boolean? And coerce it. And it turns out that Postgres is very kind in how it allows you to input Booleans. So this is, I hope, an exhaustive list. But you can see that we might throw an exception here. And this kind of function is something that you build up with blood and sweat and a lot of tears. Connection pooling, right? With libpq, every time you send a request over the wire, you cannot use that connection for any other requests. You have to wait for a response to come back. So that means while we're looking up the session for this user, we're blocked. We can't do any other HTTP requests because they're also going to need to look up sessions. So what we're going to do is create lots of connections. Postgres is limited to maybe about 50 usually. So maybe we'll create 5 per process. And then we're going to pool them, and we're going to just try to keep track of any open connection that we can use. So we have implemented database connection pooling. ORM and DB modeling. So I'll show you an example of our original code. So we have an app model here. And what we ended up doing is we have this PPX. And on one graph, an app has things like a name, a description, an org it belongs to, that kind of thing. Just a standard, type. Getting this into Postgres is a tremendous amount of work. And getting it out is a tremendous amount of work. It's very much like writing buckle script bindings, but for everything. You have to figure out how to bind everything. So what this PPX does is actually walks over the types and figures out how to decode and encode everything. It then generates a bunch of helper methods, and it does one other nice thing, which is if I open up the app SQL file, it actually parses a SQL file over here on the right, and these will become functions that we can call inside of OCaml that are inside of Reason Native that are fully type safe, efficient. It feels very comfortable. But this was not what we started with. We started with those array of strings, and we started with a lot of crashes in production whenever we got the decoding wrong. Whenever it turns out that actually you can represent true with a 1 sometimes. There are other things that we drop down, and we make good use of Postgres. Postgres is one of the most amazing open source bits of technology today. We make heavy use of triggers, notifications, and stored procedures and whatnot. Basically, we are deeply aware of Postgres, its feature sets, and very much how it works. All right, but assuming we get that request, we got the session, we are ready to start parsing our GraphQL query. So that's what this is going to look like. The step one is going to take this incoming HTTP request and some additional context. And we're going to do this deferred, don't wait for, try log. This try log is a logging library that we had to build ourselves. We have some caching and memoization here, and then eventually we execute, or we parse the query. But we can't actually execute it yet. We might need some secrets. So whenever you're making a call to us, GitHub's API requires an OAuth token. You have to be authenticated to use it. So we store an OAuth token in the database. And we don't want to store it as plain text. We need to encrypt it at rest. That means we need to encrypt it, and then at this time, we need to pluck it out of the database and decrypt it. This is a little module we wrote on top of some of the crypto libraries for Reason Native. And this makes good use of phantom types from Ben's talk. The idea being, in the Clojure world, I did something similar to this. But what would happen is, I would forget at some part of my code if I was dealing with an encrypted value or a decrypted value. And I would sometimes encrypt it twice, which is great because it's now twice as secure. But it would mean that I would decrypt it and show, a only one-time encrypted value to the user in some place, and it would be very difficult to track down. So in this case, this was a little bit frustrating to write because, who wants to focus on, well, there are people who deeply enjoy focusing on cryptography. I am not one of them. But it was really cool to be able to model this problem using the built-in language features of Reason to make it so that we don't have to think about it. We dove down deep, we became deeply familiar with it, and now we don't really have to worry about it. So that part, I would say, nice. So we've parsed our GraphQL document. We've talked to the database. We've deserialized, reserialized, encrypted, and decrypted. We're ready. We can execute our GraphQL document. So let's take a subset of that query. We'll take a simple one. This is just going to hit the npm API. This is an incredibly useful query. Given the name of the package, it will go into npm and retrieve the name of that package. It actually uses the network for that. Very good. All right, so we need to use a HTTP client. We're going to use CoHTTP. This is the main HTTP client in Reason Native. So, it's a little bit of a quick test for you. Here's an API URL. Here's another one. Anyone tell me the difference? It's just that one character, right? Can't be that much more difficult. Can't be. How difficult could it be? So, raise your hand if you know what SNI is. Raise your hand if you want to know. Raise your hand if you want to know when you're trying to ship a product today, and you have to know what that is. So, what happened was Zendesk is one of the APIs that we talked to, and they were having some issues with DDoS and whatnot, so they rolled out Cloudflare. And Cloudflare presented its TLS certificates in a way that CoHTTP didn't know how to deal with. So we could no longer make HTTP calls to any Cloudflare fronted API. We had to actually go and figure out what is SNI and why is this blocking our product development. This is challenging. So the way we fixed that was to avoid it. We thought, that's fine. We'll just bind to libcurl. Libcurl, curl's amazing, right? Super useful. There are, you can use that as a library, use it programmatically. So we pulled in the ocurl library, but we use async, not LWT. So we had to write our own backend for ocurl to use with async, which meant we had to understand how does async actually implement async. What the hell is a file descriptor? Like, why am I thinking about file descriptors whenever I'm making calls over HTTP? And what that ended up doing was we could actually make calls to Zendesk now. We were successful. But if we made more than 5 at a time, we did something wrong. The file descriptors and async and HTTPF would get upset and our process would crash. So we solved this by just booting up a bunch of instances, and they could just crash and it would be load balanced between them, and that was fine. You know, in the meantime, until this was fixed. So this has been fixed now, and CodeHP continues to be a great library. Unless you need to submit forms, right? Anyone need to submit forms? That's not a thing we do very often. Anyone know about multi-part encoding? How many of you have read the RFC and been excited to implement multi-part encoding? I tried to get my co-founder to do it, but he was not excited, so I spent a couple of my weekends implementing it. This is an example. This is not the actual full implementation, but this is how you talk to Mailgun, which is a nice API that will send emails on your behalf. They want you to use multi-part form encoding, and so I basically just looked at the data as it went over the wire from working implementation, and just figure out what is the bare minimum thing I can do to get this thing working. Yeah, so that's my Mailgun. OAuth. So we need to calculate signatures for OAuth. Twitter, for example, is very thorough about how it wants you to talk to its OAuth API. Most of the time, if you're an NPM, you just pull in that Twitter package and it would just work, right? But today is your lucky day. You're going to get to learn about the OAuth standard. You're going to learn about the ordering of parameters. You're going to learn how to make sure that you sign everything correctly. And never mind about shipping that product today. I'm sure that you're going to learn today. So then finally we get to, we've made our request upstream, we figured all this out, we put in the hard work, the results are coming back, and now we're kind of in our land. It's okay, we don't have to talk to any outside world anymore. Now we're going to start to canonicalize, figure out were there any errors from any of these API calls. We're going to structure it in a way that the GraphQL client asked for, and we'll calculate some metadata about how performant were we, how much time did we save, that kind of thing. But every now and then, OCaml and Reason are not pure. They have these things called exceptions. And exceptions have stack traces, usually. You actually have to enable this. This is by default. OCaml doesn't actually throw a stack trace because who wants that? It slows down your program. And we all know performance is a feature. So, stack traces, they may be too expensive for us to afford. But we decided we would bite the bullet. We're the user in this case, and we'll pay the price for that. So we turned on stack traces. And now we're going to be able to solve our problems. Whenever that server crashes, we're going to know what to do. This is our stack trace. This is a real one. Standard lib is, in pervasive, this is OCaml itself. And these two other lines, I don't know what they are. They're not our code. This is a real stack trace that we had to deal with. So this was, good. Whenever this popped up, we're like, all right, let's think very hard about where this might have possibly occurred. And package management, right? npm install, bundler. This is a solved problem, right? Packages, everyone has packages. Super easy. This was one of the most painful parts of building a Reason native application, was getting reliable builds across two different laptops. However, this one has been solved. I would say that this one is one that we didn't have to work on. Easy has made this fantastic. They have basically solved all of our problems, and I would prefer to use this over, say, even like Clojure or Clojars or Maven or whatnot. It's great. All right, so what's the point of all that? We did a lot of effort to be able to process a simple GraphQL request. Well, our goal, or my goal anyway, is to kind of tame some of this chaos. I want to bring some structure to these unstructured APIs. I want to have lots of control over my process. I want to know whenever things break down, how to fix them. So we've kind of made this, this progression where initially I was like, for every API that we talk to, we are going to write out a strict type definition. We're going to know every type of that upstream API. And we used ATDGen for that, which is a fantastic project. It's advanced type definitions, and it will generate a nice client for you. However, it turns out that not every API provider shares my own desire for strict types. So a lot of them were very loose. You know, sometimes the type would be there, sometimes it wouldn't be, sometimes they'd just change it. So we had to learn how to be flexible with what we got from them, but to provide guarantees to our users. And then we had to generate lots of clients for, to talk to these different APIs. We actually have a large code gen pipeline written in Clojure that reads type definitions for upstream APIs and then generates hundreds of thousands of lines of reason code that we don't have to write. But then we get to do things like where we start to canonicalize. So this is one of the things I'm most proud about, kind of taming that complexity. So whenever you call into any API on OneGraph, we recognize if you are not authenticated based off of the upstream response. So we know how to interpret Spotify's way of saying that, Salesforce's way of saying that, or Stripe's way of saying that, which is all different. But then we can canonicalize that into one kind of error message. And so this means that you have one function as a client that you can hit. So you write one function that says, what are the errors of that response I just got back? Is there an error of type missing off? If so, what's the service? Cool. I'm going to ask the user, that thing you just tried to do, turns out we need to log into GitHub. And now you don't have to do any sort of contextual, like figuring out what you're authenticated, what you're allowed access to. You just check this one set of errors, and you're good to go. So we can start to kind of tame the complexity of the upstream APIs in that way. And any production service is going to go through several layers or several migrations. And we started off originally using LWT and CoHTTP for both the client and the server. We worked for about a year, laying down, writing the multi-part stuff and the database stuff, and we got ready. We're close to launching to production. And it occurred to one of us that maybe we should do a load test. We should see if that's okay. So we fired up very, very confident, and we put siege against our service, and at about 50 concurrent requests, it segfaulted. Completely crashed. And we were going to launch the next day. And so I thought, well, that is bad, right? So we actually ripped out LWT, which is an async library, and brought in async. We used HTTP-AF instead of CoHTTP for our HTTP server. We became deeply familiar with a lot of these lower level things that we were not planning on becoming deeply familiar with. And it worked, which is great. And there were some trade-offs. We couldn't, ship to unikernels anymore. And I would say that this sucked. This was not working on product. This was yak shaving at its most furry yakness. However, I will say the cool thing about it was that it was possible. LWT and CoHTTP were at the heart of our application. It was threaded through everything. And trying to migrate to a different kind of async programming from that would have been almost impossible. Except that we were able, with OCaml, to bring in async library, change some types, and then go and fix the 650,000 places where it broke. But once it compiled, it took 3 days. And then it worked. It was great. It compiled. We threw siege at it. Boom, no segfault. Handled it like a champ. So they're definitely interesting trade-offs. I want to give a demo of why this is important to me. So, we've put a lot of effort into all of this. What's it all for? At the end of the day, what does using OneGraph look like? So what I'm going to do is query into Spotify. I'm going to search. So let's do this, add a new query. Call this one search. It's going to go into Spotify. It's going to search for a track. Let's do you and I. And any tracks that match that, I want to get the ID and the name. And I'll run this. And notice how this popped up? That's because it's reading that auth missing auth. And it's just, one function. And so I'm going to go ahead and log into Spotify. I want to run that. There we go. Cool. But let's add some mutations. Let's do resume. And this is going to do a mutation. This is going to change the world a little bit. It's going to resume my player, and then having modified my player, it's going to give me back the new state of it. So I want to know whether it's playing and its progress. And we'll just add 2 more real quick. So we'll do pause. Same idea. We'll go into Spotify. Pause my player, give me the new player back, is playing in progress. Last one, we'll say next. So Spotify, skip next track, and then I want to know, what you're playing, the progress, and let's get the name of the song that you're now playing. And now it's kind of like, it's built up this UI where I have these different operations in here that I can run. And this is pretty cool, because we can actually analyze the AST of this, which OCaml is pretty good at, right? If anything, if OCaml is good for anything, it is for analyzing abstract syntax trees. And what we can do is actually generate a full React application for this. So you can see over here that it has generated all of my React components, and they line up here. And we can do cool things where, like, a lot of people don't know that you can name your operation. So you can see we name it unnamed query, and we tell you, hey, maybe you should consider giving this a name. So we can do deep analysis and provide a really nice experience. So what I'm going to do is copy this, and I'm going to go over into Chrome, where I have a code sandbox. I'm simply going to paste this in and hit save, and there we go. It says, hey, you're not logged into Spotify. So let me go ahead and open up Spotify. Oh man, if only those were in Reverie, that would have been so much faster. All right, so put these side by side, and I'm going to go ahead and run my search query. It's going to ask me to log in. And there we go. I have a full React component that's working there, and I want to maybe, let's play this, and I want to hit next. There we go, it's doing next. I want to pause it, and I want to resume it. I have a full Spotify player that I was able to just kind of click my way through their API and then copy and paste it, and I have a full application. And as of 30 minutes before yesterday's workshop, we now support generating an entire Reason React app that will do the same thing. So this is a Reason React app. And part of the reason that I'm motivated is I do like Reason. I really like the experience. But it cannot stand on its own. Reason has to be able to talk to databases. It has to be able to talk to APIs to actually be useful. And that's part of what OneGraph does, is it actually allows APIs to be typed in a way that gives you this beautiful experience whenever you're actually building a Reason React app. You can auto-complete your way through the APIs across the internet. It's a big deal. All right, so I'll go ahead and close up. So I think OneGraph and all simple web apps are really iceberg products, where there is so much engineering that we rely on, that we take for granted, to get something that's actually usable. And part of the challenge in Reason Native is that you don't get to ignore it. You are going to become deeply familiar with every layer of your stack, whether you want to or not. And so that raises the question, if you're building a product, if you're building a company, where do you invest your time? Do you invest in polishing out a tech stack? Do you already have product market fit, or do you need to be iterating on your product faster? Do you invest in building up a community, right? Maybe you shouldn't be working in a library. Maybe it's important that you get other people. Maybe you'd want to scale out. And if people stick around long enough in Reason, then we will have lots of good benefits. So things like easy. GraphQL PPX. GraphQL PPX is magical in how nice it makes Reason to use and talk to an external API. OCaml GraphQL server. I don't know how you could build a GraphQL server that would be taken seriously without OCaml GraphQL server. Sangria is another good one, but having used GraphQL.js, it is incredibly difficult to keep any of that in sync. The types become very unmanageable very quickly. Other things like OCaml TLS, which is a pure implementation of all of TLS in OCaml. There are some really stupendous packages and some really great work that has been done inside of the Reason world, but we do need a bigger community in order to sustain that. So I want to thank these people definitely. And I'll close on this mark that OneGraph would be very, very, very difficult to build without Reason. It might even be impossible. We have hundreds of thousands of lines of code. We have types all over the place, and we have people who use it day to day that would be very upset if we broke it. But productionizing Reason has been a journey, and it's a journey that we've had to take, and it's a journey that you will have to take if you decide to use Reason Native in production. Maybe someday the community will be bigger, and you won't have to as much, but for today, that is a cost that you'll have to be aware of. Thank you.